So what I'm going to introduce to you now is a different way of looking at the equations of motion. We've done it algebraically, and we've done it with calculus, and we've decomposed some vectors, and we've looked at 2D launching of things. And now I'm giving you this vector representation of the motion. And for many people, this can be really intimidating to see at first, and I want to show you that there's nothing to panic about here. So what we have is we're given this function that says that this S vector describes motion in this thing we call y hat, or I hat rather, minus 3t cubed j hat. And what I want to convince you of is that this is easier than when we have to break everything into components, because what this expression is telling you is you know exactly what it's doing in the x and you know exactly what it's doing in the y. No trig. So let's see how we can rewrite this where it looks a little bit more familiar. Another way I could say that is that my position function in terms of time in the x is 4t, and that my position function in terms of y is negative 3t cubed. That's all that says. So if I'm given something like this, all the rules that applied before still apply now. We can like remind ourselves and say, come on, there we go. Let's undo that, shall we? Try that again. There we go. So we can remind ourselves that, let's see, I'm given x, and here's t. So if I look at this, remind myself that the change in x, so the slope of this line, is the change in x, my rise, over my run, over dt, which is a derivative. So the first question I'm asked for is the resultant velocity. Well, for that, if I can figure out the velocity in the x and the y, then I can figure out how fast it's actually going. If I put a little radar gun on it, that's what I would read. So all I need to do then is take the derivative of both of these functions. So then I can say then d by dt, let's make a note over here, I'm going to do my x, of 4t, well that just gives me 4, because remember this is a 1 in the exponent, so pull that 1 down, 1 times 4 is 4, and then I'm going to subtract 1 from the 1 in the exponent, that gives me 0, so it's just 4. So that's going to be 4 meters per second in the x. And then in the y, what do I have? If I take the derivative of it, I have d by dt of negative 3t cubed. So again, I'm going to pull the 3 down, erase that so it's not so messy. I'm going to pull the 3 down and multiply by the 3 in front. So I get negative 9t, subtract 1 from the 3 in the exponent, that gives me 2, so 9t squared meters per second. That's my units. Okay, so I know the velocity functions. Now I want to define what is its velocity at 4 seconds. So what's nice is I look at the x, and what that tells me is that the velocity is constant in the x, which is common with projectile motion, right? I have to have a force that changes the direction of the motion or the magnitude of the velocity to make that change. And if there's no air resistance, then my velocity in the x is going to stay constant. In the y, though, my velocity is changing with time. So that means I do have acceleration in that direction. But we can apply it then, let's see, so for my x, so my x of 4, is what I want it for, is just 4 meters per second. And my y of 4, let's see, that is negative 9 times 16. I'm going to do a calculator. I'm a little too tired to do math in my head right now. 9 times 16. It's 144. Ooh, it's moving. Meters per second. Cool. So the magnitude then, the resultant velocity, is still going to be, as you can think of this, I have a coordinate system. All that's told me is I'm going to go out in the x4 and then up in the y a ton. So my resultant velocity is going up like that by a whole bunch more. That's not scaled at all. So I have, whoops, I forgot my negative sign. Negative 144 squared plus 4 squared. You just write it like that. Now, what some of you found out last week was you thought when you square this, we're going to get a number really close to 144. 44 squared plus 16. And one of the misconceptions some of you walked away with was that meant that the thing that dominates, or the only thing that matters, is what's happening. I think last week we had it, the larger velocity was in the x. Yes. And so you thought just the magnitude of the velocity of x gave you the actual velocity. And that was just by chance. And the same thing is happening here. Because if I look at this, I take the square root, I get 144, and I'm going to write it out to the decimals. All this says is that 144 squared plus 16 is really friggin' close to 144. That's it. So when I take the square root of it, I'm going to get back nearly identical to the number I put in there. That's it. Under all other circumstances, those numbers are different, and it will matter that you do the actual square root of everything. Okay, so that is the resultant velocity. That answers the first question. Let's do some units. And then the second question is, oh, velocity at 2 seconds. Oh, the acceleration. Okay, I thought there was two different things going on there. So we want the acceleration at 2 seconds. Okay, so I have velocity, and you might think of this and be like, well, I was given a position function. Well, what happened? I took the derivative of it, and I got velocity. So if I go over here, now I have a function. I can rewrite this. Let's go v of t. Actually, not as a function. Let's write it in vector form. That should be an eraser. Then I'll have my velocity vector is going to equal then 4x hat minus 9t squared y hat. Where all I've done there is gone from I hat to x hat, j hat to y hat, to put it in something that you're used to seeing. They're interchangeable. There's no difference between the two. It's just a lot, more the advanced mathematics like to use ijk instead of xyz. Okay, so here, there we go. Now I have velocity here and time here. So I look at the area under the curve is meters per second times seconds. Oh, that gives me displacement, which makes sense because an integral is like an antiderivative, and I took the derivative of the position function to get to velocity. So all I would be doing is putting myself back where I came from. And I look at the slope though, and my slope, rise over run, meters over seconds, and then over seconds, so that gives me acceleration. Okay, so I need to take the derivative again of this in order to get my acceleration. So let's see, d by dt, here's my x component, just to be clear what I'm doing, of 4. There is no t, so that is 0, which should be, because if the velocity in the x is constant, there is no acceleration, the answer should be 0. For my y, I have this negative, let me be good with my notation, d by dt of negative 9t squared. Pull the 2 down, I get negative 18. T, 2 minus 1 is just 1, so my acceleration is described as negative 18t. Therefore, the only thing I have for my acceleration function, so my acceleration vector, if I wanted to write it like that, I would have 0 in the x-hat minus 18t in the y-hat. So I want to evaluate it to see what its acceleration is. The magnitude of its acceleration isn't dependent on x at all. So whatever I evaluate this at, I'm essentially doing the same thing, we just don't show the step, where I'd be squaring it and taking the square root of it, so I'm just going to get whatever that answer is. So at t equals 2 seconds, I get negative 18 times 2, let's see if I can do that in my head, negative 36 meters per second squared. Now you notice I'm not worrying about what my units are living inside of these functions. I know what they are for acceleration and velocity. As we progress, we'll worry about paying attention to the units and what the units need to be to make sure that we come out with the correct ones. On the last quiz that we did, you notice that they had some bizarre units, like seconds to the fourth. That's so in the end we would actually get the correct units that we needed for the quantity being described. So there you have it. We have taken a vector function and derived both its velocity and its acceleration from that. Let's do more.